At the heart of a black hole is a singularity, an infinitesimal point in space where the pull of gravity is infinitely strong and space-time infinitely curved. At the singularity, space and time no longer exist as we know them. So what would happen if we traveled into one? To answer this question, let's look at a simple black hole, one with mass but doesn't spin or have any electric charge. This animation shows our descent. At the lower left is a graph showing our trajectory. The green region is a safe zone where our spacecraft orbit around the black hole is stable and we can still get out. The yellow region is a risky zone where our orbit is unstable. Here, a short burst of our maneuvering thrusters will send us either into the black hole or off into outer space. The orange region is a danger zone where there are no possible orbits for our spacecraft, stable or unstable. To remain in orbit in this zone, we must constantly keep firing our rockets. The closer to the horizon we get, the harder we must fire our rockets to keep from falling in. The red line is the horizon. From here, there is no escape. At the bottom right of the animation is a clock, which records the time left until we arrive at the central singularity. The clock records our proper time, the time we experience, the time on our wristwatch. In this animation, the clock slows down not because time is slowing down, but because it is more interesting to run the movie slower nearer the singularity, so that we can see more clearly what happens here. As we begin our approach, we can immediately see the distortion of light around the edges of the black hole. This is the gravity well bending light, lensing the light from the background stars into long circular arcs. The event horizon is depicted as a red grid. This marks the boundary beyond which nothing can escape, not even light. Notice that we can see both the north and the south poles of the black hole simultaneously. Since the black hole bends light around it, we can see all around and into the back of the black hole at the same time we see the front. This horizon is called the Schwarzschild radius. About 3 Schwarzschild radii marks the location of the innermost stable orbit, the green area in our trajectory. Here, circular orbits are stable. Beyond, they are unstable. Any material accreting around this black hole finds its innermost edge here. Anything slightly closer falls into the black hole. So long as we remain in this region, we can still get out. At about 2 Schwarzschild radii, we reach the risky zone, an area of unstable orbits. Any slip up here, such as a small firing of our thrusters, would randomly send us either headlong into the black hole or flying away from it. Also in this region, we arrive at a special location known as the photon sphere, the distance where light rays can remain in orbit. This is the closest to the black hole that anything can get and remain in orbit. For our rocket to stay here, our thrusters would have to expend an infinite amount of energy. As we fall through the horizon at 1 Schwarzschild radius, something quite unexpected happens. Instead of falling through the red grid that marks the horizon, it stands off ahead of us. The horizon splits into 2 distinct entities, the horizon and the anti-horizon. Light from both of them hit us as we pass. The true horizon becomes visible only after we have fallen through. The anti-horizon continues to remain ahead of us, and we never fall through it. It is a common misconception that if you fall inside the horizon of a black hole, you will be engulfed in blackness. What happens instead, the universe appears brighter and brighter as you approach the horizon, tending to infinite brightness at the horizon. By this time in our journey, however, none of us would be able to sense any of this. Once inside, space is falling faster than light, carrying us inexorably inward. Here, we are now at 0.8 Schwarzschild radii. As we fall, in a typical sized black hole such as ours, the tidal forces are weak enough that we can fall deep inside the horizon before we are torn apart. The gravity at our feet is stronger than the gravity at our heads. We feel this difference as a tidal force, which pulls us apart vertically. At the same time, we are crushed in the horizontal direction, like a rubber band being pulled. Finally, as we approach the singularity and we look up one last time, we see that the intense gravity of the black hole has concentrated the view of the outside universe into a thin band around our waist. The views above and below are dim and redshifted, while the view around our waist is bright and blue-shifted. We never actually get to see the center of the black hole because all light is rushing towards it and none away from it.